Hi everyone, my name is Yuantian, and today I'm presenting our work titled A Concurrent Approach to String Transformation Synthesis with Xiaokang from Purdue University. And let's first introduce a bit about syntax-guided synthesis. Syntax-guided synthesis is a process that aims to automatically find a program that satisfies a certain specification. Normally there are two inputs for cycle solver. The first one is semantic specification, which defines the program should do, and another one is syntactic information, which describes what the program should look like. Normally use a context-free grammar, and the cycle solver normally just takes those two inputs and generate a solution. The application for syntax-guided synthesis are like spreadsheet programming, and like computer-aided education, complex supermodulation, and loop invariant discovery. And for the SMT solvers, a cycle solver also supports a range of theories, including CLIA, bit vector, and string. And for methods to solve cycles problem, we often use enumeration, deduction, and learning-based methods. And it's a quite active field of research. In past 15 years, researchers have built a lot of solvers in cycle solving, like Flashfield, Sketch, and CVC5, and a lot of others. And researchers have also made a lot of improvements to existing solvers. Like, for example, for the ICFP benchmark, at the year of 2015, only 1 of 50 benchmarks can be solved. But now solvers can solve all of them. So likewise, the hike-delight benchmarks. Despite the existing process of cycle solver, we still find some problem with string transformation synthesis challenging, even though it's already a well-researched field. So let's first look at a motivating example. In this example, we need to standardize addresses from different countries. Each address must follow the same format, which is country/region/city/street/unit. As highlighted, some address may or may not include a unit number, which add a little bit complexity here. And the solution should be quite simple. It first splits the examples into two parts, in two cases, and then just rearrange them with with all those comma-separate components. However, surprisingly, this simple task is not solvable by existing cycle solvers, including CVC5 and Flashfield++. So let's discuss the problem. So the first challenge is the number of operators. For string, you have a lot of operators available, like concatenation, substring, and replace. And for list line, and if you have list and integers with a string, you will have some other operator like join, index, and format int. And even for a single, and even for this is only just standard operator, you will have some other operators like domain-specific operator, dates, time, and floats, etc. And even for a single operator, you will have a lot of different ways to split the problem, which is P1. Like for concat, you may have a lot of ways to divide the problem. Like the P2 and P3 two problem, you may split before the slash and after the first slash. And like some other problem like P5, you may split the second example but ignore the first. Because all those different ways of split, it's quite challenging for cycle solver to get this problem solved and make the search space quite large. So because of this problem, we propose to utilize concurrency to rescue, by which we mean to use enumerator to communicate with the deducer in order to steer the deducer in a more promising path. Because the communication process of the enumerator and deducer is concurrent, so we call our framework Synthphonia a concurrent synthesis framework. So let's start with some animation. So imagine our original synthesis task as P1. Our solver will try to break this task down using different operators like concat and join. Each operator will try to split the problem into some subproblems. However, because there are a lot of operators and a lot of different splits, we don't know how to proceed. So we run some enumeration to get this process. So first, we start a single enumerator to help select the most promising deduction. We run the enumerator for a while, and the enumerator finds an expression which is T1, and it's shown to be a prefix of P1. And using this expression, we can see that we can deduce P1 using the concat operator. So we run the deduction and we simplify the problem P1 into the problem P2. And similarly for problem P2, we can also deduce it with a lot of different operators. And we again take all this possibility to enumerator and try to use enumeration to get some hints. And this time we found another expression which is T2, which is a constant and a substring of both P1 and P2. So based on this hint, it's okay to guess that T2 can be a kind of separator because it's a constant. So because it's separator, we can deduce P1 and P2 using the join operator, which is becoming P3 and P4. So our framework will recursively deduce those P3 and P4 until the problem is solved. So let's now illustrate more about this framework on a motivating example. So the deducer starts with the original problem, which is P1. And for example, to deduce this problem, we may use the join operator. So it asks the enumerator to find a constant substring of P1 to split the original problem using join operator. And it may also ask about other operators like concat. So it will be a question like, can I have an expression that produces any perfect P1? So while sending a lot of those questions to enumerator, enumerator can handle all of those questions simultaneously. And after some while, it found an interesting expression which is slash. Using this, expression is a response to the join operator. So when the deducer meets this expression, it further deduces P1 using join operator into P2, which is a list of components from P1. And we can further ask some questions from P2, but here we simply ask if P2 can be solved by enumeration alone. And this will be quite hard because P2 need a lot of rearrangement of the inputs. So the enumerator can't find a good solution shortly. So it returns this before that it found, which is guiding to another promising path. So this time it's an expression which evaluates to the country code with UK, Australia. And with this expression, P1 is further deduced into P3, which is basically a concat operator, and remove the country code at the beginning. And we continue this process and ask some other further question about perfects. And then we ask, it responds another one, and we ask another one. And just repeat this process. As we can see, it can, Yeah, by repeating this process, we can see it will be finally solved. So then we show the entire architecture of our solver. So our architecture consists a asynchronous deducer, which considers each deduction asynchronously with some communication with the enumerator, and a versatile enumerator, which kind of multiple requests, allows some requests from the deducer simultaneously with a single enumeration. It's also worth noting that to do this, we need a special data structure called term dispatcher. For this part, if interested, you can refer to our paper. So among all those operators, if then else is especially hard to deduce using our method, because the enumeration doesn't really help to deduce this operator. Normally, we want to deduce if then else operator as a decision tree, but what kind of decision tree? If we focus on a small decision tree, it will be pretty hard because it probably doesn't even exist. You have a lot of terms, and these terms need a lot of deduction enumeration. And if you try to do a larger decision tree, like in the right-hand side, it will be much easier, but it's very likely to be an overfit because you arrange this decision tree out of nothing. It's basically a guessing. So, and the existing approach like EU solver doesn't really handle this problem. So it basically separates term search and condition search, like in this picture, in this figure. and while ignoring the balance of the two. So we want to propose our idea to solve this problem in our setting. So here our approach is basically to use a decision tree learner, which is constantly trying to learn a larger and larger decision tree by constantly increase the set limit. And we also have a worker which constantly generates new terms and conditions and add to a pool for the decision tree learner to learn a new decision tree. So the worker will constantly trying to make a smaller decision tree, but the tree learner will try to learn a larger and larger decision tree. So at some point, these two search will meet in a middle point, and which provide a solution. This solution, as we can imagine, if possible, it will be pretty small, and it will use as much as term and conditions as possible. So actually, the tree learner is actually use basically a linear function to respect to the time to increase the set limit. And for the worker, it's basically, just as I mentioned before, it's a pair of deducer and enumerator. And we also need a pool to share the condition and pool to the condition and solution to learn the decision tree. And let's look at the example for this. So it first ask ask an example for the worker to ask if it can try to solve this example. And if it's solved, we can use that for decision tree learning. So the worker is responds with T1, which solves not only E1, but also another two examples, which is E3 and E5. And at the same time, we also increase the decision set limit. And at the same time, other worker can also return some conditions and expressions. Like here, it returns C2 C1 in response, which separated E2 from other examples. Because the problem is still not yet solved, it's still impossible to learn the decision tree. So we put another example with E2, and we obtained T2 in return, which solves this bunch of examples. And because all example is solved by a single term, but it's still impossible to learn a decision tree, so we put two examples into the worker, trying to solve them jointly with a single term, and also trying to find additional conditions to help to split the problem. So actually it got T3 in return, which solves those E2 and E5, but some other example also solved, but it's still not useful to obtain a solution. So we continue to do this, and we obtain another condition C2. With this, it can generate a decision tree. So we put this to a decision tree learner, and we obtain a solution like that. That's basically the idea of our accumulative case splitting to rescue the problem of the balance of solution conditions. So now let's discuss our experimental results. So our implementation is called Synthphonia. It consists approximately 7,000 lines of code written in Rust. It's pretty easy to implement with language features like async and await. To access its performance, we'll compare Synthphonia against several existing solvers, yet not all the solvers have the same support for grammar. So for the fair comparison, for those solvers support only standard grammar, like staggered if. We compare those solver with a version we call Synthphonia G, which is basically a more limited grammar, which only supports staggered if grammar. And for FlashFill++, which have a richer grammar, we use our for solver for comparison. So let's now talk about benchmarks. This pie chart illustrates our benchmarks, which are drawn from three main sources. So which is Doit, Harbinge, and Pros, all with their unique characteristics. And we also provide some test case for generality check to ensure the solution doesn't overfit the results. And let's now look at the experimental results. Synthphonia significantly outperforms existing solvers in our setting. As shown in figure A, it solves 116 benchmark uniquely, and in figure B, it solves 531 benchmark outperforming other solvers, and in figure C, it observed a faster time compared to other solvers. And we also conduct some ablation study with respect to cumulative case splitting, asynchronous deduction, and multi-threading. And it's showing that all of them provide some performance gains to our solver. So that's all for our solver. Thank you. So any questions? Oh yeah, we compare with it. Like, but at time of this work, we compare to GPT-4o, so we still can beat that one. But you know, with the reasoning model, our method become very weak. So yeah, we will figure out the problem later. Yeah.
Thank you for the great talk. So the accumulative case splitting approach, can it also be used for synchronous setting? So like you can use some sort of round robin method for multiple workers. So.
Oh, what kind of like?
Like you try to solve the overfitting problem.
Yes.
In the accumulative case splitting approach. So can it also be used for synchronous setting? Synchronous setting of using multiple workers, like using round robin approach.
Yeah. Do you mean like just do a, like one thread kind of thing, not like multi-threading, use one worker? Yeah, it works. Like here we have the
SP1
version.
B is for that. The figure B is the case when you use a synchronous setting.
I don't know what exactly you mean by synchronous setting. I mean, if we are talking about just one worker.
No, like I was just thinking of using a single thread, but like there are multiple workers. Like, I mean like.
Oh, okay, I see. Yeah. That's probably not benefit too much, I guess, because because you know you already have. You can simply do a multi-threading, right? If you're doing that, so that's not something our solver considers. So. Yeah, but you know, as even proven that even for one thread solver, we can beat the flash field plus. Okay. So, yeah, we didn't consider that because we have multi-threading.
Thanks for the answer.
Yeah.
Any other question? Okay, let us thank the speaker again.
Okay.